Hi there, how are you doing? So the last time we talked about how to calculate the E-note cell, right? So now let's see how we can compare these E-note half cell values. We learn about the standard electron potential. They normally refer to the half reaction as a reduction. Okay, the value E-note value will be given to us as a reduction. E-note values therefore reflect the ability of the reactant to act as an oxidizing agent. Remember, the reduction, the species that are undergoing reduction is the oxidizing agent. So they are normally given as the ability of the reactant to act as an oxidizing agent. The more positive the E-note value, sometimes you will have more positive values or more negative values. Look here, the more positive the E-note value, the more readily the reactant will act as an oxidizing agent. Okay, the more negative the E-note value, the more readily the product will act as a reducing agent. The more negative E-note value, reducing agent, the more positive E-note value will act as oxidizing agent. And here are some standard electrode potentials. Okay, remember they are all given in terms of reduction. All of these are taking up electrons, meaning the standard electrode potential is written as a reduction. Okay, so you can see these values, positives, and then here you have the hydrogen, the standard one, and then the negative values. Now you can go down, it increases the strength of the reducing agent. The more negative the standard electrode potential, they are strong reducing agents. And going from here to here, it increases the strength of oxidizing agent. So these guys here, they act as good oxidizing agents, and these ones here act as good reducing agents. The more negative the value, better reducing agent. More positive the value, better oxidizing agent. So in other words, more negative ones would be, if they are reducing agents, they are good at oxidation. Okay. Writing spontaneous redox reactions. Each half reaction contains both a reducing agent and an oxidizing agent. Right? So you take two half reactions, each one has a reducing agent and an oxidizing agent. The stronger oxidizing and reducing agents react spontaneously to form the weaker ones. Just like strong acid and strong base gives you weak acid and weak base. If you have a strong oxidizing agent and strong reducing agent, their reactions will be spontaneous and they will form the weaker ones. Remember, a spontaneous redox reaction, E-note cell needed to be greater than 0. Okay, will occur between an oxidizing agent and any reducing agent that lies below it in the EMF series. So this is the electromagnetic force series, EMF series. That is one that has a less positive value for E-note. So our goal is to get E-note cell greater than 0 for a spontaneous reaction. So in order that to happen, oxidizing agent and any reducing agent that lies below it in the EMF series. One that has a less positive value for E-note. The oxidizing agent is the reactant from the half reaction with the more positive E-note half cell. Oxidizing agent. So these are the oxidizing agents. As you go up, the strength of the oxidizing agent increases. As you go down, the strength of the reducing agent increases. Okay. So the reducing agent is the species that are undergoing oxidation. Oxidizing agent is a species that would undergo reduction. Oxidizing agent will undergo reduction. Reducing agent will undergo oxidation. Let's look at some examples. Using half reactions to write a spontaneous redox reaction. So you are given two reactions. Tin 2 plus. So both of these are given as reductions. That is the standard way of writing the equation. Tin 2 plus taking 2 electrons become tin, negative 1.14, and silver ions take 1 electron becoming silver solid. That's also written as reduction, that is 0.80. Now our goal is to get a positive value for the E note cell. Remember, E note cell is E note cathode minus E note anode. Step 1, reverse one of the half reactions into an oxidation step so that the difference between E note values will be positive. Here the silver plus silver half reaction has the more positive E note value. So it must be the reduction. The more positive one would be the reduction. Okay. Reduction happens at the cathode. This half reaction remains as written. So because the more positive one is going to be the reduction, you're going to keep it as it is. So we don't have to reverse it. We reverse the tin 2 plus tin half reaction, but we do not reverse the sign. So we reverse this because now this need to be the oxidation. So tin 2 plus plus 2 electrons. You reverse this, remember, to half reaction. One has to be oxidation, the other one reduction. So this is the reduction, this is going to be the oxidation. Now we're going to reverse this reaction, but we don't reverse the sign. E note tin will remain as negative 0.14 volts. If you were given two reactions like that, use the more positive value for your reduction, more negative value for the oxidation. Okay. And then the step 2. Multiply the half reaction if necessary so that the number of electrons lost equal to the number of electrons gained. So here you have 2 electrons. Here you have 1 electron. So we need to multiply this by 2. We multiply the equation but not the value for E naught. E naught will not be doubled. We just multiply only the reaction. 2 silver plus 2 electron giving you 2 silver solid. And then we're going to add the reactions together, cancelling common species. So tin 2 plus 2 electrons, keep E naught negative 0.14, and silver reduction, keep the E naught silver value. When you add up, your 2 electrons will get cancelled, and then the remaining complete reaction would be this, the balanced one. So how do you calculate the E naught cell? Remember, the E naught cell equals E naught cathode minus E naught anode. Cathode is our silver because that's where the reduction takes place, 0.80, minus 0.14, which is going to be your anode. So negative will make it positive. 0.8 plus 0.14 is 0.94. So E naught cell is 0.94, which is positive. So now the reaction is spontaneous. Okay. Here's another example. 3 examples in fact. Combine pairs of the balanced half reactions 1, 2 and 3 into 3 spontaneous reactions A, B and C and calculate E naught cell for each. Combine pairs of the balanced half reactions. So we are given E naught cell values. Now we're going to find out, we are going to calculate E naught cell for each at the end. How are we going to do? Now the first one, nitrate ion with 4H plus with 3 electrons, nitrogen monoxide and 2 water molecules. Now we are given 3 equations. All of these are given as reductions and these are going to be their E naught values. We are going to combine pairs of balanced half reactions. We're going to combine 1, 2 and 3 into 3 spontaneous reactions A, B, C and calculate E naught cell. So we can take 1 and 2 first, these two. If you take these two, if you're going to combine these two, to make a spontaneous reaction. This one E naught 0.96, this one E naught negative 0.23. Which one is going to be the oxidation? Which one going to be the reduction? Remember, for the oxidation, we choose the one with the more negative value. For the reduction, we choose the one with the more positive value, because E naught cell would be E naught cathode minus anode. So this, if this is the cathode, this is the anode, cathode minus 0.23 going to give us a positive value. So this is going to be your oxidation, this is going to be your reduction, and this reaction need to be reversed. And then we need to multiply if needed to make the electrons balanced. So the first one, nitrate 4H plus 3 electron. This reaction you're going to write as it is. Okay. For 1 and 2, equation 2 has a smaller, less positive E naught value. So this guy, you reverse it. N2H5 plus, you reverse this second one and written it as a oxidation. You see this one. Now N2H5 plus is the reactant. But when you reverse it, you don't reverse the E naught value. And there are 4 electrons, 3 electrons. So we need to multiply this by 4, this by 3. 1 by 4 and 2 by 3. So you do the multiplication, the whole 2 reactions. But we don't multiply these two. And your E naught would be cathode minus anode. And your cathode is the reduction, which is this guy, 0.96 minus the anode minus 0.23. So 1.19. Right? So this is a spontaneous redox reaction. And then we can do 1 and 3. So between 1 and 3, 1.96, 3, 1.23. So between 1 and 3, which one is going to be your reduction? Which one going to be your oxidation? Always the reduction would be the more positive value. So then the reduction would be 1.23 and then the oxidation would be 0.96. So 1.23 minus 0.6 will give us a positive value when you calculate the E naught, right? Okay. For 1 and 3 equation, 1 has a smaller, less positive value. So this guy is going to, the less excuse me, positive value will be the one that undergoing oxidation. So you reverse that equation, but you don't reverse the value. You see, and the third one, you're going to keep it as it is. There are 2 electrons, 3 electrons, so you multiply this by 2, this by 3. So you have those balanced equations. So when you add it up, 6 electrons get cancelled, and this is going to be the balanced equation. And E naught cell would be cathode minus anode, and your cathode is going to be where the reduction takes place, which is 1.23. Higher positive value cathode minus the anode 0.96. So now the E naught cell is greater than 0.27. Excuse me. That's a spontaneous reaction. Okay. And then we're going to look at 2 and 3. So 2 and 3, E naught negative 0.23, 1.23. So which one is going to be your oxidation? Oxidation going to be the more negative value, and this is going to be your reduction. That's where the reduction takes place, which is going to be your cathode, right? Cathode minus anode minus 0.23, that will make it positive, so it would be 1.46 E naught cell positive. This is going to be your reduction and this is going to be your oxidation, and we will reverse this reaction between 2 and 3, right? 2 has a smaller, less positive E naught value. So this is going to be your oxidation. You reverse this reaction. And then you're going to keep this as it is. 4 electrons, 2 electrons, multiply this by 2. So the number of electrons are the same, and this is the overall reaction. And this is where the oxidation takes place, anode, and this is your cathode. E naught cathode 1.23 minus 0.23, 1.46 volts. Okay. That's how you would make a spontaneous reaction by looking at the E naught values of individual half reactions. The activity series of the metals, strong reducing agents. Remember, the strong reducing agents are the ones that would undergo oxidation. Excuse me. How do you find out a metal is more active or not? We're going to look at the activity series. So metals that can displace hydrogen from acid are metals that are stronger reducing agents than hydrogen. So here you have acid taking up 2 electrons, becoming hydrogen gas, and then the iron become iron 2 plus and 2 electrons. So in this case, E naught cell going to be cathode minus anode. This is going to be a cathode, 0 minus 0.44, positive 0.44 volts. The lower the metal is in the list of half cell potentials, the more negative its E naught half cell, and the stronger it as a reducing agent. So these are the half cell potential series that we talk about. Remember I showed you earlier, the lower the metal. You see here, the lower the metal. So these guys who are below hydrogen, they act as strong reducing agents. In other words, these are the species that would act as oxidation in our half cells. And these ones will undergo reduction if they are combined with any of these metals. Okay. Yeah. The more negative the E naught half cell of a metal, the more positive its E naught cell for the reduction of hydrogen ions, and the more active a metal it is. Weak reducing agents. Metals that cannot displace hydrogen from acid are metals that are weaker reducing agents than hydrogen. So silver here, silver plus and 2 electrons, 0.8, hydrogen kept as 0. The higher the metal is in the list of cell potentials, the more positive its E naught half cell, and the weaker it is as a reducing agent. The more positive the E naught half cell of a metal, the less positive its E naught cell for the reduction of hydrogen ions, and less active a metal is. Metals that can displace hydrogen from waters. There are some metals, for example sodium, you put it into water, it can form sodium hydroxide and hydrogen gas. They are stronger. Metals that can displace hydrogen from water are metals whose half reactions lie below that of water, meaning they are going to be stronger reducing agents. And this is the reaction for the water, and this is the reaction for the sodium. So sodium will act as the oxidation, and then the water will undergo reduction, and the E naught cell 2.29. In order to reduce water to hydrogen, the metal should have a more negative E naught half cell than water, like this, more negative. We can also predict whether one metal can displace another from solution. Any metal that is lower in the list of electrode potential has a more negative E naught value, will reduce the ion of a metal higher up the list. Between zinc and iron, so negative 76, negative 0.44. So these two Which one going to act as the oxidation? Oxidation will happen in zinc and reduction will happen in iron, because this has a more negative value. The more negative value will undergo oxidation. So your E naught cell going to be cathode minus anode, and this is your cathode, minus 0.44 minus 0.76. So this would become positive, so 0.76 minus 0.44, 0.32. Okay, E naught cell. Reaction of calcium in water. Calcium, you put it into water, it will become calcium ion. And then what happened to the water? Water takes up 2 electrons and give out hydrogen gas and hydroxide ion. And then the overall reaction would be 2 electrons are going to cancel out, calcium plus water, giving us calcium hydroxide and hydrogen gas. Now we're going to see how we can relate free energy and electrical work. For a spontaneous redox reaction, meaning delta G gives free energy less than 0 and the E cell needed to be greater than 0. And we can give this equation delta G equals negative NFE cell. N here is the number of moles of electron transferred and F is the Faraday constant, which is this value. And then the E cell, we know how to find the E cell. Under standard conditions, we say delta G naught equals negative NFE naught cell. Okay. And E naught cell equals another equation, RT. R is the gas constant, T is the temperature, N is the number of moles, F is the Faraday constant, L N K. K here is the equilibrium constant. Substitute 8.314 for the constant R. Substitute Faraday constant is here. And then substitute 298.15 Kelvin for temperature under standard condition, keeping in mind that the cell can run at other temperatures. And then this explains how you can get this equation from this equation. E naught cell equals RT NF ln K, or you can say E naught cells by substituting these values that is given here. R gas constant, temperature, this temperature, N is number of moles 1 and this is the Faraday constant. And then once you get that, converting ln to log, multiply by 2.303 to convert the natural logarithm to common base 10 logarithm. This conversion shows that a 10-fold change in rate constant makes E naught cell change by 1. So when you put all these values here and multiply by 2.303 ln K, you can come up with this equation. E naught cell equals 0.0592 volts over N, number of moles. We can change it here later depending on the number of electrons. And then the log K. And this is the temperature, 298 at 25 degrees Celsius. And this is called the Nernst equation. So one equation that we can connect delta G and E cell, delta G equals negative NF E cell. And then we can also connect E naught cell to K equilibrium constant using these two equations. The relationship of delta G naught, E naught cell and K. Delta G naught and K can be connected using delta G naught equals minus RTL and K. And delta G naught and E naught cell can be connected using delta G naught equals negative NF E naught cell. And E naught cell and K can be connected using E naught cell equals RT NF ln K. Delta G less than 0, K greater than 1, E naught cell greater than 0, that's a spontaneous reaction. If delta G naught 0, E naught cell 0, K equal 1 at equilibrium. If delta G naught greater than 0, K less than 1, E naught cell less than 0, that is non-spontaneous reaction. Calculating K equilibrium constant delta G naught from E naught cell. Silver occurs in trace amounts in some ores of lead, and lead can displace silver from solution. Lead plus 2 silver ions, lead 2 plus 2 silver ions, 2 silver solid. As a consequence, silver is a valuable byproduct in the industrial extraction of lead from its ore. Calculate K and delta G naught at this reaction, at this temperature for this reaction. Now, this is the spontaneous reaction given to us. So we can see lead is becoming oxidized. Lead oxidize and silver reduce. We divide them into divide the spontaneous redox reaction into half reactions. So these are the half reactions with their E naught values from the appendix. Silver ion, when it is written as reduction, E naught 0.80. Lead written as reduction, E naught 0.13. Now between these two, this is more negative value. So lead becoming lead 2 plus would be the reducing agent or the oxidizing species. This would be oxidizing and this would be reducing. Okay. So we need to reverse equation 2 and multiply equation 1 by 2. We reverse this one because it's the oxidation. Lead becoming lead 2 plus 2E. We don't do anything to the electrode potential. Silver going to remain as it is as a reduction. This needed to be multiplied by 2 to make these two electrons equal. And then this is the overall reaction, and then E cell would be cathode minus anode, and this is going to be your cathode and this is your anode. Cathode is where the reduction takes place and this is the anode. 0.80 minus 0.13. So that would be 0.93 volts. Spontaneous redox reaction. So we found the E cell. What we want to find out is the calculate K and delta G naught. Okay, and then we calculate E naught cell. We were not given E naught cell here, we calculated that. So to find out the K, we can use E naught cell equals RT over NF ln K, which is similar to 0.0592 volts over 2 is the number of electrons 2, that's N log K, which is 0.93 because we found E naught cell 0.93. So the thing that we don't know in this equation is the K, so we can find K. So then the log K would be 0.0592 over 2 okay, the other way around. So log K is this side. So then the log K would be 0.93 times 2 over 0.0592. Okay. Log K is 31.42. So then the K would be 10 base 31.42, which is 2.6 into 10 to the 31. So from the E naught cell, you can find the equilibrium constant using the Nernst equation. And then we need to find out the delta G naught. We can use this equation, negative NF E naught cell. N is the number of electrons, which is 2. And this is the Faraday constant, and E naught cell 0.93. So we can find that also. Negative 1.8 into 10 to the power 2 kilojoules per moles per reaction. Okay. So this example shows you if you were given a reaction with the E naught half cell values, how to find out the E naught cell, and how to relate E naught cell to K and E naught to delta G naught and find out these values. So the Nernst equation, E cell equals E naught cell minus RT over NF ln Q. So if you want to find out E cell, any other condition other than the standard cell, you can use this equation. E cell equals E naught cell minus RT NF ln Q. Q is the reaction quotient. When Q less than 1, reactant concentration is more than the product. Remember, Q is the concentration of products over reactants. So ln Q going to be in that case less than 0. So E cell going to be greater than E naught cell. When Q equals 1, reactant concentration and the product concentrations are the same. ln Q going to be 0. So E cell, so these two would be equal. This side is going to be 0. E cell equals E naught cell. When Q greater than 1, meaning reactants concentration is less than the products, ln Q greater than 0, so the E cell would be less than E naught cell. We can simplify the equation as before. For temperature 298.15 Kelvin, E cell would be E naught cell minus, and this whole thing would be with this constant negative 0.0592 over the number of moles of electrons log Q. Let's put that into an example. In a test of a new reference electrode, chemists construct a Voltec cell consisting of zinc 2 plus half cell and hydrogen H plus half cell under the following conditions. Zinc ion concentration given 0.01, hydrogen 2.5 molar at 0.3 atmospheric pressure. Calculate the E cell at 298.15 Kelvin. So we can use this equation, E cell equals E naught cell, and this expression. So to apply the Nernst equation and determine E cell, we must know E naught cell and Q. We write the equation for the spontaneous reaction and calculate E naught cell. Right? It is zinc 2 plus and hydrogen plus. So this is going to be E naught for the hydrogen electrode, and this is for the zinc. Zinc would be the one that would undergo oxidation because it has higher negative value. And this is the complete reaction. So cathode minus anode, E naught cell 0.76. So to find E cell, we know E naught cell. Now we need to find out the Q. Q is the reaction quotient, concentration of products over reactants. So our products are going to be zinc ions and hydrogen. Zinc, ion and hydrogen. And we are given the concentration, hydrogen and zinc. And this is a solid, we don't put solid concentration, and H plus ions given to us. And then the pressure also given, 0.3. Hydrogen ion concentration 2.5. So we can find out the Q. So Q, pressure for hydrogen, zinc concentration and hydrogen ion concentration. Partial pressure for hydrogen was given as 0.3. This is H plus and this is zinc ions. Zinc 2 plus 0.01 and H plus 2.5. Raised to the power 2 because it was 2H plus. So Q can be calculated by this ratios of concentrations and the pressure, 4.8 into 10 to the negative 4. So we can use now that equation, E cell equals E naught cell, which is 0.76 minus this value log 4.8 into 10 to the negative 4. So 0.86. So E cell is 0.86. Okay. That's how you can calculate E cell from a given reaction. Concentration cells. Concentration cell exploits the effect of concentration changes on a cell potential. The cell has the same half reaction in both cell compartments but with different concentrations of electrolytes. For example, you have two copper solutions. Copper solid giving you copper 2 plus in a 0.1 molar solution, releasing 2 electrons, which is oxidation, happens at anode. And another aqueous medium, copper 2 plus, again 1 molar, takes up 2 electrons and become copper solid. That is the cathode. So overall reaction would be, that's right. So this is 0.1 molar, this is 1 molar. You see there is a difference in the concentration, 0.1 molar, 1 molar. The lower concentration one would be the oxidation, higher concentrated one would be the reduction. So copper 2 plus 1 molar, copper 2 plus 0.1 molar. As long as the concentration of the solutions are different, the cell potential is greater than 0 and the cell can do work. So we need to have two different concentrations. So this is a diagram of the concentration cell based on the copper 2 plus half reactions. So this is the anode with the lower concentration. What is happening? Copper becoming copper 2 plus, and then the 2 electrons, lower concentration solution, 2 electrons gonna go to the other side, which is the cathode, and then 2 electrons will be taken up by the copper 2 plus ions in the solution and deposited as copper. Okay. And then after some time, you will see this side of the copper where you have the lower concentration, 0.1, the copper metal would be less, and then the other side, the cathode copper, would become higher in weight or become bigger because the more copper is deposited here, cathode. Okay. So in your oxidation half reaction would be the one with the lower concentration, copper solid giving you copper 2 plus 2 electrons, and then the higher concentration one would be the reduction, copper 2 plus 1 molar solution taking 2 electrons become copper solid. Overall reaction would be copper solid will get cancelled, copper 2 plus 1 molar solution will become copper 2 plus 0.1 molar solution. That's the overall cell reaction. Let's put that into practice with an example. A Voltaic cell consists of two silver plus half cells. In half cell A, the electrolyte is 0.01 molar silver nitrate. Half cell B, it is 4 into 10 to the negative 4 molar silver nitrate. What is E cell at 298.15 Kelvin? So there are two silver nitrate, 0.01 and 4 into 10 to the negative 4. So this is the higher concentration and this is the lower concentration. So the lower concentration one would be your anode, higher concentration one would be your cathode. The standard half cell potentials are identical. So E naught cell is 0 because both of these are silver. So E naught cell 0. And we find E cell from the Nernst equation. Half cell A has a higher silver concentration. So silver ions are reduced and played out on electrode A, which is therefore the cathode. Remember, the higher concentration one is the cathode where the reduction takes place. In half cell B, this guy over here, silver atoms of the electrode are oxidized and silver ions enter the solution. As in all Voltaic cells, a reduction occurs at the cathode, so it is positive. The silver concentration decreases in half cell A and increases in half cell B. So our spontaneous reaction would be silver ions 0.01 molar half cell A becoming silver ions in the 4 into 10 to the negative 4 molar half cell B, similar to the copper one. So we can use this equation E cell equals E naught cell, and the Nernst equation, this value log Q. Q is silver ions in the diluted solution over the silver ions in the concentrated solution. E naught cell would be 0. Why? Because both of these are silver, right? So if you have the silver value, you subtract the same number, that would become 0. And then this value over here log diluted solution is this 4 into 10 to the negative 4, concentrated 1.01. You find the log value of this one, and then when you calculate, we can find out the E cell 0.0828. Spontaneous reaction. That concludes our session on electrochemistry.